Why are design load calculations important to a structural engineer? Structural engineers try to consider the effects of loads on three basic design characteristics. First is structural stability. A stable structure is one that has been designed in equilibrium with the elements that may apply force to the structure. Next is strength. Strength refers to the ability of a structure to withstand applied loads. For example, the materials used are not stressed to their breaking points, and there is room in the calculations to ensure safety. A structure must have stiffness with a degree of flexibility also. If a structure has strength but not stiffness, it may deform too much when a load is applied. The third common characteristic is economic value. Economic value affects choices made about time, materials, and energy consumption. Often the correct choice is not necessarily the obvious one. Therefore, alternatives should be considered and thoroughly researched before decisions are made. A structure should efficiently and safely resist all types of forces. Structural loads are the result of natural forces and include the following. Dead loads are very important to consider and are the only fixed or unchanging loads on a structure. Live loads are variable elements but must be estimated. The third type of load is wind. Wind load is also dynamic in nature because wind pressure, direction, and duration are constantly changing. Wind loads are treated as lateral loading on walls and vertical loads on roofs. Impact loads, shock waves, or vibrations can come from natural phenomena and liquefy the ground beneath the structure. Seismic loads are earthquake-related forces that can shake a structure apart. The choice of materials is very important in planning a design that will withstand different load-bearing situations. In most cases, designers use load tables to determine the forces they must consider. In this lesson, we will focus on dead loads, live loads, and their reaction forces. The live loads are variable elements including people, snow, and movable furniture. The dead loads are fixed elements or material the structure is made of, including roofs, ceilings, walls, utilities, floors, and foundations. Finally, reaction forces are those that come from the ground and supporting structural members. Determining structural efficiency can be accomplished using the formula shown, and is one way to compare various designs of a structure. Safety margins are also commonly designed into a structure. Multiplying loads by a predetermined factor will increase strength and stability. However, for our examples, we will not include any safety factors in our calculations until the very last step. Beams and girders can be supported in a variety of ways. Beams can be supported at both ends, at several points along their length, or at just one end. Since simple beam types are the most commonly used, we will use this type for our example problem. Different beam supports create unique reaction forces. Pin connections create reaction forces in the X and Y direction, while roller connections allow for movement in the X direction and create reaction forces only in the Y direction. Fixed supports create moment or rotating forces which are a product of the applied forces and their distance from the supported end. These diagrams show the distribution of three typical uniform, concentrated, and combination loads. The type of loads need to be identified before calculations are made. The formulas used to find reaction forces and moments for each distribution are not the same. Columns are vertical members designed to withstand compressive forces of loads from attached beams and girders. The columns transfer loads from all upper levels, including the roof, and apply them to the concrete footing. We will now use this simple single-level steel frame building to demonstrate how to chase the loads. However, these procedures apply to any size or level structure. These are the general steps we will follow to chase the loads and in the end find an acceptable size structural member for each part of the design. First, we'll lay out, label, and dimension the concrete footing and steel structural members. Then calculate dead loads, live loads, and their reaction forces. MD Solids will provide us options of structural steel choices. Next, we'll evaluate our choices in relation to various constraints. Lastly, if needed, we will change our design to better meet our needs. These are the structural elements commonly used to chase the loads in a design. The load pathway usually starts at the top of the structure with an interior beam. Beams are used to support the live and dead loads from a floor or roof. These are attached to girders, which are stronger and can be used to support multiple beams. Next, we load the exterior beams of the building and with the girders connect to the vertical columns. After we load the column, we determine the size of the concrete pad that spreads the load out on the ground. First, we need to lay out, label, and dimension the structural members in a plan view. The design area will be for the longest interior beam because it usually holds the heaviest load. The space we will use for determining beam loads is called the tributary area, as it is the entire roof space the beam must support. For our example, we will be determining the loads for beam C23. The width of the tributary area is known as the tributary width, and in our case is 6 feet 0 inches, the same as the beam spacing center to center. The girder and column in the load pathway are also identified in the diagram. The structure we are chasing the load on is a simple one-story steel frame building. We'll start by determining the dead loads. In this list you'll find the materials that make up the roof and their respective weights for 1 square foot of material. By adding these weights we get the preliminary dead weight total of 32 pounds per square foot. Next we find all of our live loads, which will only be snow as there are no people or furniture needs for a roof. Since we need to start somewhere with an estimate of the weight of the beam, we'll choose a standard W12 by 16 I-beam. The tributary width and span, or length of the beam, were determined from the preliminary layout we've already finished. With our known data, we can now calculate the loads on the beam. By adding the dead and live loads, we can multiply them by the tributary width to find the loads on top of the beam. We need to include the weight of the beam as it must also support itself, and this total becomes our uniform load for the beam. This 328 pound per foot load is a force applied every foot the entire length of the beam, thus determined to be a uniform load and designated load W. Once we know the uniform load, we can find the downward force and reaction force at each end of the beam. We can use this formula for finding reaction forces from uniform loads. The load times the length of the beam divided by 2 will give us the reaction force at the end of the beam. We will use this 2,624 pound force to eventually determine the loads applied to the girders and columns. Determining the maximum bending moment, which is a product of force times distance divided by 8, gives us the bending force of the beam. Later we will use the 10,496 foot-pound moment to find the section modulus, which is the resistance to bending. MD Solids can be used to verify our calculations. Everything checks so far. Next we'll need to find the uniform loads on the exterior beams of the structure. These typically have half the tributary area. We will also use the previously estimated beam weight where all the beams are sized to carry the maximum load at any point in the structure. By multiplying the 172 pound per foot uniform load times the 16 foot length of the exterior beam and dividing by 2, we get the reaction force for the end of the exterior beam. These loads and resultant reaction forces will be applied to the girder. MD Solids is used again to check the calculations. In order to find the section modulus, or resistance to bending, we first must find the allowable bending stress. In order to not overstress the steel, we are going to multiply the 36,000 pound per square inch maximum yield strength by 0.67 and get an allowable bending stress of 24,000 psi. The section modulus, or resistance to bending, is very important. Using the beam's maximum moment and multiplying by 12, we convert our moment to inch-pounds. We then divide by the allowable bending stress, and this equals a 5.248 cubic inch minimum section modulus. We have now generated enough data to allow MD Solids to give us some choices for structural members. First, we input the moment, shear or reaction forces, and allowable stress values. These are then computed to verify our results for the section modulus located inside the blue oval. This will supply us with a list of beams from which to choose. These are generally listed from lightest to heaviest, but also have different characteristics. Lastly, we need to determine the maximum beam deflection allowed. This is done to ensure there will be no cracking of materials, sagging, or roof drainage problems as the beam flexes under load. First, we multiply the length by 12 to convert it to inches, then divide by 360. This gives us a maximum deflection of 0.533 inches. From our previous calculations, we determined the beam needed to have a minimum section modulus of 5.3 cubic inches and a maximum deflection of 0.533 inches. MD Solids provided us with a list of possible beam choices with which we can investigate. After analyzing all the choices, the W10 by 12 beam is the best fit of those listed on the chart, as it meets both criteria. Now we'll chase a load from the beams onto the center girder. The concentrated loads on the girder load diagram represent the ends of the two beams attached at opposite sides of the girder and 6 feet from each end. Since each beam has a reaction force of 2,624 pounds, the total concentrated load on the girder at that point is 5,248 pounds. The uniform load in this example is the estimated weight of the girder per foot and goes the entire 18-foot length. Since we have a combination concentrated and uniform load, we can use the formula shown. The sum of the first concentrated load and the product of the uniform load times span can be divided by 2 to find the reaction or shear force at the end of the girder. By our calculations, this is determined to be 5,464 pounds and will be used shortly to find the total loads on the column.